Good evening, classmate. Good evening, Sir Ryan Montilla. So, our topic is all about Chapter 2, An Introduction to Linear Programming. So, we are the double A partner.
Linear programming, an overview. Objective of business decision frequently involve maximizing profit and minimizing cost. Linear programming uses linear algebraic relationship to represent affirmed decisions given a business objective and resource constraints.
So, these are the table of contents. 2.0, An Introduction to Linear Programming. So, linear programming has nothing to do with computer programming. The use of the word programming here means choosing a course of action. So, linear programming is a problem solving approach developed to help managers make decisions. So, in Introduction to Linear Programming, a mathematical used to obtain an optimum solution in resource allocation problems such as a production planning, or it is a mathematical model or technique for efficient utilization of limited resources to achieve organization objectives, maximize our profit, or minimize costs. When solving a problem using linear programming, the program is put into a number of linear inequalities, and then an attempt is made to maximize or minimize the inputs. Constraint optimization model have three major components. So decision variables, objective function, and constraints. So a decision variables, it is controllable input for a linear programming model, and it's physical quantities that controlled by the decision maker and represented by the mathematical symbol. Next is the objective function. It is the evaluation criterion. It also defines the criterion for evaluating the solution. Or it is a mathematical function of the decision variables that converts a solution into a numerical evaluation of the solution. Constraints are the physical, economic, technological, legal, ethical, or other limits on what numerical value can be assigned to the decision variables. Constraints are a set functional equalities or inequalities that represent it all, or other restriction on what numerical values can be assigned to the decision variables.
Linear programming problems. The maximization or minimization of some quantity is the objective of all linear programming problems. All linear programming problems has constraint that limits the degree to which the objective can be pursued. A feasible solution satisfies all the problem constraints. An optimal solution is a feasible solution that results in the largest possible objective function value when maximizing or smallest when minimizing. It is a feasible solution that has most favorable value of the objective function. The optimal solution obtained is optimal for the specific problem formulated. A graphical solution method can be used to solve a linear program with two variables. It is limited to linear programming models containing only two decision variables. Also, it provides visualization of how a solution for a linear programming problem is obtained.
If both objective functions and constraint are linear, the problem is referred to as a linear programming problem. So linear function are function in which each variables appear in separate terms raised to the first power. It is our straight lines that we know the coordinates of the 2 points. We can graph the line. So a function of f defined by f of x is equal to ax plus b, where a and are the real number. So linear constraint are linear functions that are restricted to be less than or equal to or greater than or equal to a constant. If all the terms of a constraint are of the first order, the constraint is said to be the linear. So this means the constraint doesn't contain a variable squared, cube, or raised to any power other than 1. A term divided by a variable or a variables multiplied by each other. Also, proportionality must exist. In other words, for every unit increase or decrease in a variable, the value of the constraint increases or decreases by the fixed amount. So the linear programming model is a mathematical model with a linear objective function and a set of the linear constraint and a non-negative variables.
Constraint, an equation or inequality that rules out certain combination of decision variables as feasible solution. Constraint are restriction or limitation on decision variables. Non-negative constraint, a set of constraints that requires all variables to be non-negative. Suppose a constraint has a negative right-hand side. When you achieve consistency between the solution of the problem with the observed reality, and in order to avoid implausible solution to a linear problem, non-negative constraint variables must be added. So redundant constraint, a constraint that does not affect the visible region. Its removal would not alter visible solution space. Feasible region is the set of all feasible solution. It is all defined by the set of constraint of the problem, which is all possible points that satisfy all the constraints.
Extreme points are the feasible solution points occurring at the vertices or corners of the feasible region. So the feasible set of for the linear program will always have a shape with edges that are straight line and corner where the edges meet. So the corner of the feasible set are called extreme points. Next is the decision variables. It is controllable input for a linear programming model. And it's also called or also known as divisibility. And it is allowed to take on any real numerical values within some range specified by the constraint. And that is a variable are not restricted to integers value.
Slack variable is the amount unused resource. It is added to the formulation of linear programming problem to represent the slack or idle capacity. Surplus variable is the amount of over and above some required minimum level. So these represent an excess of constraint requirement level. Surplus variables contribute nothing to the calculated value of the objective function.
2.1 A simple maximization problem. Problem formulation and mathematical statement. So, problem formulation and modeling is the process of translating a verbal statement of a problem into a mathematical statement called the mathematical model. In this way, we can solve life and business problems using the mathematical method. Formulating is an art that can only be mastered with practice and experience. So every linear programming has some unique features, but most problem also have common features. So kung may use man ta og mathematical equation, we can calculate the right or probable answer sa atong problema kung naaman. So let's go to example that we have provided for you. Power Incorporated is a small manufacturer of golf equipment and supplies whose management has decided to move into the market for medium and high price golf bags. So Par Distributor is enthusiastic about the new product line and has agreed to buy all the golf bags Par and produces over the next 3 months. After a tree investigation of the steps involved in manufacturing a golf bag, management determined that each golf bag produced will require the following operations.
So these are the following processes of making the bags: the cutting and dyeing, sewing, finishing, inspection, and packaging. So they are processing of standard bag and deluxe bag are given, and the available time for production of bags are given as well.
Let us now develop a mathematical model of par incorporated problem that can be used to determine the number of standard bugs and number of deluxe bugs in order to maximize the total profit contribution.
So let us now have the solution. So identify the decision variables or the controllable input for a linear programming model. Let us now choose the unknowns. What are the missing points in this problem? It is the total profit contribution of the standard bug and the deluxe bug. So in this problem, our decision variables are the deluxe bug and the standard bug. Let S be the number of the standard bug and let D be the number of deluxe bug. And since our objective is to maximize the total profit contribution, so we will write as the maximum total profit contribution is equals to 10S plus 9D, or F of S and D is equals to 10S plus 9D.
So this now the mathematical model of our problem and its constraint maximize total profit contribution. Then S plus 9D subject to this constraint, the 7 over 10S plus D less than or equal to 630, 12S plus 5 over 6D less than or equal to 600, S plus 2 over 3D is less than or equal to 708, and 1 over 10s plus 1 over 4d is less than or equal to 135. So s and d is greater than or equal to 0.
2.2 Graphical Solution Procedure. So since we already encounter linear function from our previous years or math subject, most of us already know how to graph linear function. Since linear function are straight lines, so we knew the coordinates of 2 points. In this graph, we will use the constraints to determine the feasible solution. Graph shows the line of limitation according to the constraints. So mauni siya ang feasible region or the set of constraints. Naa siya sulod sa limitation given by the problem. So there is a limitation for hours in cutting and dyeing, sewing, discussing, finishing, inspection, and packaging, in which mauna siya ang form sa feasible region. So to continue,
This is the summary of graphical procedure. So first, prepare a graph of the feasible solution for each of the constraint. So means imong itagsa-tagsa o graph ang constraint like making a line for one constraint on linear function. So number two, determine the feasible region by identifying the solution that satisfy all the constraints simultaneously. So imo i-determine ang feasible region that which lies inside the constraint or limitation given. Number three, draw an objective function line showing the values of the decision variables that yield the specified value of the objective function. Number four, move parallel objective function lines that towards larger objective function values until further movement would take the line completely outside the feasible region. And lastly, any feasible solution on the objective function line with the largest value is an optimal solution. So the optimal solution is the feasible solution that has most favorable value of the function. It is the largest possible objective or the smallest when minimizing. This step will be discussed further on the next slide.
2.3 Extreme points and optimal solution. So mauni siya ang graph to get the optimal solution. So the line there inside the feasible region is an objective function line or the profit line, since our objective is to get the maximum profit. So mauni siya ang step 4 wherein the profit line move parallel towards the larger objective function or the maximum profit line until the further movement would take the line completely outside the physical region. So mauna siya optimal solution. So let us now go to the step 5. So let us substitute S to 900 minus 10 over 7b is equals to the equation 1 times 900 minus 10 over 7d plus 2 over 3d is equals to 708. So let's just do the mathematical equation and we will derive to the answer of 252 as b. So to get s, substitute d to the equation. So s is equals 900 minus 10 over 7d times 200. S is equals to 900 minus 10 over 7d times 252. So we will have 540 as an answer. So we have to produce 252 deluxe and 540 standard pack to attain the maximum total profit contribution.
2.4, computer solution of bar incorporated problem. Computer programs designed to solve linear programming problems are now widely available. After a short period of familiarization with the specific features of the package, users are able to solve linear programming problems with few difficulties. So, problem involving thousands of variables and thousands of constraints are now routinely solved with computer packages. Some of the leading commercial packages include CPLEX, Jurobi, Lingo, Mosaic, and Resolver for Excel and Express MP. Packages are also available for free downloads. So a good example is the CLP or the coin or linear programming. So now let's go to the 2.5, the simple minimization problem. M&D Chemical produces two products that are sold as raw materials to companies manufacturing both soap and laundry detergents. Based on an analysis of current inventory levels and potential demand for the coming months, M&D's management is specified that the combined production for product A and B must total at least 350 gallons. Separately, a major customer's order for 125 gallons of product A must also be satisfied. Product A requires 2 hours of processing time per gallon and product B requires 1 hour of processing time per gallon. For the coming month, 600 hours of processing time are available. So M&D's objective is to satisfy these requirements of at a minimum total production cost. Production costs are $2 per gallon for product A and $3 per gallon for product B. So in this problem, our objective is to minimize total production cost.
So let us now have the solution for this minimization problem. So identify the decision variables as what my partner said earlier, decision variables or the controllable input for the linear programming model. Let us now choose the unknowns. What are the missing points in this problem? So the missing points is the minimum cost production schedule. So our objectives or the decision variables, let A is equals to the number of gallons of product A and let B is equals to number of gallons of product B. So to write the objective, minimum cost of production schedule is equals to A plus 3B, or F of A and B is equals to A plus 3B.
This will be the graphical solution procedure for the minimization. So same lagi happens sa maximization of process. So first is prepare a graph of the feasible solution for each of the constraint. So in this graph, the constraint were plotted that way, and the blue shaded portion is the feasible region. Number two is determine the feasible region by the identifying the solution that satisfy all the constraints simultaneously. So to draw a line for the object function, then i-move nimo ang parallel line to the smallest object function line value to get the feasible solution on the objective function. So the line with the smallest value is an optimal solution. So same ra jud siya sa process sa maximization, but they just differ on the part nga ang pangitaon sa maximization is the largest value of the feasible region, while the minimization is the smallest value of the feasible region. So alternative optimal solution. I mean, the 2.6 is the special cases, alternative optimal solution, infeasibility, and unbounded. Alternative optimal solution is the case in which more than one solution provide the optimal value for the objective function. Infeasibility is the situation in which no solution to the linear programming problem satisfies all the constraints. So in real life, we often face situation in which it is impossible to satisfy all the restriction confronting us. Unbounded is if the value of the solution may be made infinitely large in a maximization linear programming problem or infinitely small a minimization problem. So sometimes the linear program has unbounded solution. In this situation, the objective function can achieve a value of positive infinity for the maximization problem or negative infinity for a minimization problem.
2.7 General linear programming notation. So to formulate a linear programming model of a par incorporated problem, we began to define two decision variables wherein S is equals to number of standard bug and D is equals number of deluxe bug. In the M&D chemical problem, the two decision variables were defined as A is equals number of gallons of product A and B is equals number of gallons of product B. We selected decision variables according to their names in S and D in the PAR incorporated problem and A and B in the M and D chemical problem. To make it easier to recall what these decision variables represent in the problem. Although this approach works well for the linear program involving small decision variables, it can become difficult when dealing with problems a large number of decision variables. This general linear programming notation is X with subscript. Like aside from using S and D for variables, we use X script 1 or X subscript subscript 2 for notation. This notation is simply to avoid difficulty, especially on more complex. For instance, in the par incorporated problem, we could use X subscript 1, number of standard bag, and X subscript 2, number of deluxe bag in the M&D problem. So same as in the M&D problem, X subscript 1 is the number of gallon of product B and X subscript 2 is the number of gallon of product B. So that ends our report.
Thank you so much, everyone. Thank you for listening here in our YouTube. So I am Andrea Marie Ancla and my partner, Alona Angel. And we are the double A partner. Thank you and God bless.